Welcome back to Introduction to Machine Learning. I am Ludwig Botmann, and in this video, I will talk about classification performance measures. We will talk about the misclassification error and accuracy, and we will talk about the confusion matrix and all the entries in the confusion matrix. Next, we will tackle the idea of costs and finally talk about the definitions of Briar Score and log loss. As you already know, in classification, we can either predict the class labels or the class probabilities. The class labels could be a M times G matrix, where M is the number of observations and G is the number of classes. So in a multi-class classification, perhaps G is larger than 2. And then we have all those one hot encoded class labels O hat, Ki, where K means the kth class and I means the ith observation. Alternatively, we can look at the class probabilities. The class probabilities will be between 0 and 1, but the dimension is the same as for the class labels. Alternatively, we've spoken about predicting scores, which we called F as well, so a minor F. And we can compute from the scores the probabilities via calibration or scaling, from the scores to discrete class labels via thresholding. We can come from probabilities to discrete labels via thresholding. So there are a lot of connections between all those three instances. But for evaluating the classifier, we will only look at the labels and the probabilities. The first two metrics I want to introduce are the misclassification error rate, MCE, and the accuracy. And those are, well, very well related. So for the misclassification error rate, we count how many false predictions we make. So we compare Y, so the true label, with Y hat, the predicted label, for each instance of the data set we use for evaluating our classifier. And then we just average this, and then we have a misclassification error rate. For the accuracy, we do more or less the same thing. We just don't count those where we have an inequality going on, but those which are equal. So we count all the correct predictions and average them over the whole data set. If the data set is small, this can be somehow brittle. So the MCE says nothing about how good or skewed predicted probabilities are. The errors on all classes are weighted equally, which is often inappropriate, and we'll tackle this later on, how to do this better in that case. As you might have guessed already, reducing the prediction errors to a simple number is not the best thing to do, and would be better to tabulate them in a so-called confusion matrix. So here you see a confusion matrix, and I will tell you how this is constructed. The true classes are in the columns, and the predicted classes are in the rows. And then we just put in the absolute numbers in the cells of that matrix. So for example, this 50 here means that we had 50 setosa, which were predicted correctly as setosa. And for example, this number 4 here means that we have 4 vesiculars, which were incorrectly classified as virginica. So we made 4 errors here. And the same holds for the other error terms here. And then we can go on computing metrics from these confusion matrices. When we go over to binary classification, then we typically call one class the positive class and the other class the negative class. Often the positive class is the more important and smaller one. And if we then reduce the confusion matrix from a multi-class classification to a binary classification, you can see this picture here. So we have true class, positive and negative, and predicted class, positive and negative. And then we have 4 absolute values in this matrix. There are the true positives. So true positive means that an instance is classified as positive, that is really positive. And false negative means that an instance is classified as negative, but it is actually a positive one. So perhaps to explain this the other way around, the positive in true positive and false positive means that we have a positive prediction. So it goes in this direction here. And vice versa, we have the false negatives and the true negatives in the rows. So that correspond to the negative predictions. And then false and true just means if we have a correct prediction or a wrong prediction. So on the diagonal, we have the true prediction, the correct prediction. So we have the true positives and true negatives there. Sometimes we have situations where different errors are differently bad. So in this cases, we can also assign different costs to different errors via a so-called cost matrix or cost function. And then we can compute the costs as average costs over the entire data set here. So let's have an example here. We have a bank which wants to decide whether to grant a loan of 10,000 euros to a person and has some features like age, income, profession of that person. So we have a classifier which predicts if a person is solvent or not. And the question is, should the bank lend the person money or not? So then there are different costs going on here. So we have the loss in event of default, which is the entire loan. And we have the loss of income through interest paid, which is much smaller. So that's 100 euros. So that's the amount of money we do not get if we don't give the loan to a solvent person. And then we can write down those costs in such a cost matrix here, which has the same structure as the confusion matrix. So with the predicted classes in the row, the true classes in the column, and then we have solvent and not solvent. And in that case, we would say that it is good to make a correct prediction. So we don't have costs here on the diagonal, but we have costs on the beneath the diagonal. So if we make an error, we have some costs, but the costs are not equally high. And with this cost matrix and a corresponding confusion matrix of the classifier, we can compute the costs the bank would have by using this classifier, which corresponds to this confusion matrix. So let's say we have this confusion matrix here. So perhaps we would say it's rather good. So we have accuracy of 90%, but we do make some errors. And then we can compute the total costs by just multiplying the costs with the numbers in the confusion matrix. So we have 100 times 7 plus 0 times 70 plus 0 times 20 plus 10,000 times 3. And this will be divided by n. So n is 100 in that case because we have 100 observations. And then we end up at a cost of 307. And then a different approach would be to just give the bank to just give the credit to everyone who wants to have the credit. And in that case, the 77 solvent persons are good and the 23 not solvent persons are bad because none of them will repay the loan. So we have 10,000 lost a cost of 10,000, and this cost 23 times. So in the end, we will end up with a cost of 2300. Until now, the performance evaluation was performed on the predicted labels, but as pointed out in the first slide, we can also use the probabilities to evaluate how good the classifier is. So one example would be the Briar score, which just measures the square distance of probabilities from the true class labels. And then we take the average of those square distances. So it's actually the mean squared error on probabilities. And the usual definition for binary case would be that yi is encoded as 0 or 1. And here at the bottom of the slide, you see just a small plot of the Briar score. So for the true label 0, we start here at 0, 0 and go up to 1, 1 in the end. And for the true label 1, it's the other way around. And at p hat equals 0.5, there is an intersection of those two class functions. We can also define the Briar score for a multi-class classification. The idea is just the same as for the binary Briar score, but we have to sum over all the classes. So K goes from 1 to G. And here the OKI marks the one hot encoded class label. And then for the binary case, this Briar score for the multi-class case is twice as large as the usual Briar score because we sum the square difference for each observation regarding both class 0 and class 1 and not only the true class. And then another measure for evaluating a classifier based on probabilities is the log loss, also known as Bernoulli or binomial loss. And yeah, you already know this one here. So we have just the y times log pi plus 1 minus y times log of 1 minus pi. And then the minus goes into that into that sum as well. And you also see a plot of the log loss here, and you see that confidently wrong is penalized more heavily than for the Briar score, because for the Briar score, this function here only went up to 1. So for the Briar score, we have for the verse prediction 1, and for the log loss, the loss can be higher than 1. So confidently wrong predictions are penalized more heavily than for the Briar score. And of course, there's also a multi-class version of the log loss, and you see the formula here on the bottom of the slide.